Hello students, today we are going to discuss the application of resonance. In the last class already we have discussed what is the resonance, what are the different structures of resonance and what are the different conditions of resonance. Already we have discussed which structure is more stable, which canonical form is more stable, which is less stable. Already we have discussed these things. Now we discuss what are the important application and the use of resonance in organic chemistry. Now first you see one important thing, change in bond length. Change of bond length. Due to resonance, bond length also changes. How? For examples, benzene, if you see the structure of benzene, benzene has double bond and single bond. But the bond length of benzene, Cc of benzene, bond length of Cc bond length of benzene is equal to 1.539 picometer. Cc actual is 1.54 picometer. C double bond C is equal to 1.34 picometer. So that indicates why the bond length of benzene, Cc bond length of benzene lies in between 1.54 to 1.34. That means greater than double bond but less than single bond due to resonance. Because if you see, this is the resonance structure of benzene. The pi bond is circulating throughout the ring. That's why it has converted to bond, is converted double bond. Now it is now double bond, it is now single bond, double bond, single bond, double bond. So if you see, double bond becomes single bond, double bond. That's why the bond length, carbon-carbon bond length of benzene lies in between single bond and double bond. This is one application. Then second application is phenol. If you see, phenol, the OH bond length of phenol, the OH bond length, COH of phenol is less than alcohol. Less than alcohol. The COH bond length, COH bond length, COH bond length. The COH bond length of phenol is less than alcohol because phenol has resonance. If you see, this is the resonance structure of phenol. So the resonance structure will be for phenol will be now double bond character between COH. As it has a double bond, CO become double bond in phenol. So the bond length, CO bond length of phenol is shorter than alcohol because alcohol has no resonance. Due to resonance, double bond character is formed. That's why bond length decreases. So this is regarding bond length of that some compounds. Third one is phenol is an weak acid. Why phenol is an weak acid? Because phenol on losing H plus ion, forming phenolate ion. Phenolate ion. This is phenolate. This is called phenolate. And this phenolate ion is stabilized by resonance. It is stabilized by resonance. Okay? As is stabilized by resonance, so the phenol has a tendency to lose H plus ion in water, forming stable phenolate ion. That's why phenol is an acid. But if you compare phenol with the carboxylic acid, which is more acidic? Carboxylic acid is, suppose COH is more acidic than phenol, CHOH. Why? Because if you see that C has 3C double bond O minus, after losing H plus from acetic acid produce acetate ion. Acetate ion is stabilized by resonance. and this resonance is equivalent resonance, which is equivalent resonance. Already you have discussed. If molecule or ion having equivalent resonance, it is more stable. So phenolate ion also resonance after losing H plus ion, and acetic acid also after losing H plus ion from acetate ion. But acetate ion is more stable than phenolate ion, because you have to see if conjugate base is more stable, then the parent acid is more acidic. Here conjugate base Cb means conjugate base of acetate ion, conjugate base of acetic acid, that is acetate ion, is more stable than phenolate ion. That's why acetic acid is more acidic than phenol. This is very important. Then another application, that allyl chloride hydrolyzes faster than vinyl. That is hydrolysis. Why the Cl can easily substituted by OH minus. Under hydrolysis, this easily hydrolyzes compared to vinyl, because this after losing HCl minus, it produce stable carbonium, stable, because it is stabilized by resonance. That's why it is more stable. As the allyl, this is allyl carbocation is stabilized by resonance. That's why this allyl chloride easily hydrolyzed, because it after loss of Cl minus forming allyl carbocation, which is more stable. That's why allyl chloride has tendency to lose Cl minus. But vinyl chloride, if it produces resonance, then what happens? Become double bond character. It has double bond character between chlorine and carbon. As it has resonance, it forming double bond direct. But if this type of resonance is not possible in case of this allyl chloride, because no pi bond conjugation to the lone pair on the chlorine. So no chance to delocalize this lone pair from chlorine, because it has no resonance. But it has resonance. Due to resonance, double bond nature is formed between carbon and chlorine. That's why reactivity is less. But here, after loss of Cl minus, becomes stable carbocation. That's why the tendency to lose Cl minus. That's why easily hydrolyzed. Phenol not easily protonated. Why is not easily protonated? Because phenol has resonance. As it has resonance, the electron density on oxygen decreases. As due to resonance, electron density of oxygen decreases due to what? Due to double bond nature of oxygen, and the lone pair delocalized towards benzene due to resonance, so electron density of oxygen decreases. That's why the attraction towards proton will be less. That's why the electron density of oxygen is decreasing due to resonance. That's why it is not easily protonated, because for protonation it should have electron density on the particular atom. As due to resonance, electron density decreases, so H plus cannot easily added. That's why protonation is difficult. But alcohol can be easily protonated, because alcohol has more electron density on oxygen compared to phenol, because it has no resonance, it has only plus effect. Due to plus effect, electron density of oxygen increases. But in case of resonance, in case of phenol, the electron density decreases. That's why it's not easily protonated. This is very important thing. Chlorobenzene Chlorobenzene is less reactive than chloroalkane, because this thing same like your phenol, as it has resonance, so electron density, so chlorine becomes double bond character. As chlorine becomes double bond character, if you see the resonance of chlorobenzene plus chlorine become plus and gets double bond character, and this is minus like this. As it has double bond character due to resonance, so reactivity is less compared to haloalkane. Haloalkane is more polar than haloarine. Haloalkane, this haloalkane is more polar than haloarine due to resonance of haloarine, so that the polarity also less. Amide, this is amide, is weakly basic. Weakly basic, that is acts as an amphoteric character, we can say. But your thalamide is acidic character. That means thalamide, the hydrogen attached to nitrogen is acidic, but this NH2 group behaves as weakly basic. Why? Because this, after losing H plus ion from this one, after losing H plus from thalamide, the product form is stabilized by resonance. This, after losing H plus ion from thalamide, this negative charge is delocalized by keto group by resonance. That's why it is more stable. Conjugate base. This conjugate base of thalamide, this is called thalamide. This thalamide is acidic character, but amide is weakly basic. So this is also one important points regarding the guanidine is strongest base. If you see, guanidine is a strongest base. Why? Because if you see the structure of guanidine, this is guanidine. This guanidine is strong base because when it accepts H plus ion, then forming NH2 plus double bond C NH2, then NH2. It is stabilized by resonance. Just you see, it has lone pair like this. So what is the first resonance of guanidine? NH2, now C NH2, then double bond NH2 plus equivalent resonance possible. As it has equivalent resonance, similarly also other structure is possible, different types of. So that's why guanidine is a strong base, acts as a but very strong base, highly basic character, because the guanidinium ion after accepting H plus by guanidine, this is a guanidinium ion. This guanidinium ion is stabilized by resonance. As it has equivalent resonance structure, so highly stable. That's why guanidine acts as a very strong base. This is also very important application of resonance. If you see other structures, that this is called pyrrole. Pyrrole is less basic than this compound. Why it is less basic? Because the lone pair on nitrogen is delocalized by resonance. As delocalization occurs, so lone pair availability on nitrogen decreases. That's why it is, because we know basic character increases when electron density on the atom increases. As the electron density decreases due to resonance on nitrogen, that's why it is less basic. And already I have told you aniline, if you compare about aniline and your alkyl amine, basic character if you compare, this is less basic, basic nature. This is also basic. Why? Because it has resonance. Electron density on nitrogen decreases, but it has plus I effect. As it has plus I effect, electron density on nitrogen increasing. Here electron density on nitrogen decreasing due to resonance. So this is the important application of resonance. Where you will utilize, it depends upon the properties changes. Amide is less basic than amine. Here amide, you see the structure of amide. Amide has resonance, so electron density on nitrogen decreases, but in case of amine it has plus I effect, so electron density on nitrogen increasing. That's why basic character is more. This is the basic nature. Basic nature of amine is more than amide because amide has resonance. This concept also very important. Then stability of carbocation, carbanion. If you see carbocation and carbanion, carbon carrying positive charge and carbon carrying negative charge. But you remember this thing that pH whole 3C plus is more stable than pH2CS plus, more stable than pHCS2 plus, is more stable than that allyl, is more stable than that CS3 whole 3C plus, is more stable than CS3 whole 2CH plus, is more stable than CS3 CS2 plus, is more stable than CS3 plus, because it is stabilized by resonance. Here 3 times of phenyl groups, resonance will be triple. 3 times of resonance, so that energy will be decreased. That's why stability is more. So any phenyl group attached to carbocation, phenyl group attached to carbanion, that is carbon carrying minus charge, phenyl group attached to free radical, in all cases it is more stable by resonance. That's why this phenyl group attached to carbon, if it has free radical, if it has negative charge, if it has positive charge, then it is highly stable. So as 3 phenyl groups, that's why number of resonance is more, that's why it is more stable. So this is the order of stability of carbocation. Acidic character, if you compare, CH3 is less acidic than phenyl. Then CCH3 is less acidic, then more acidic CH3PH, then CH2PH, and it is also highly acidic CH, pH, and pH. Because you see, if you see the conjugate base, already I have told you the substance where the acid in the conjugate base is more stable. Here the conjugate base stability This is the acidic nature, but stability of conjugate base of this stability order, that CH2 minus is less stable than CH2 minus pH. Again CH minus pH, again C minus pH. What happens? As 3 phenyl group attached to carbon minus, it is delocalized more, number of delocalization is more, that's why the carbon possesses less negative charge by resonance. So already I have told you pH means phenyl group is attracting group, by resonance the negative charge on carbon is delocalized towards benzene ring. That's why stability increases. This is very important thing regarding the stability of carbocation, carbanion. But one thing I want to tell you, HClO4 perfluoric acid is more acidic than HClO3, then HClO2, then HClO. Because if you see the conjugate base, that is ClO4 minus, this is acidic nature, and this is your stability. ClO4 minus more stable than CH2 minus, more stable than ClO2 minus, more stable than ClO minus. Because if you see this structure Cl, this is your 4 oxygen, 1 oxygen carrying minus charge, okay, and this is carrying double bond. This is your ClO4 minus, it is stabilized by resonance. Like this. How many? Another 2 possible structures. 2 structures are possible. That's the stability is more. In case of ClO4 minus, 4 resonance structure possible, 3 resonance structure possible, 2 resonance structure possible. That's why if you see the stability of conjugate base, this Cl4 or chlorate ion is more stable. That's why parent acid is more acidic. This concept already I have told you. Maybe substance may be acid or base. If its conjugate acid and conjugate base should be more stable, then the parent acid base will be more acidic or more basic. If you see that organic acids does not behave like, does not show taste like aldehyde or ketone. Why does not show the taste like aldehyde and ketone? Because it has resonance, so it loses double bond character of the ketone group. If you do the resonance, this structure is O minus, then double bond OH plus after resonance. Resonance structure you have to practice. If you are really that knowledge, you have good knowledge regarding the structure of resonance, different resonance structure, if you can draw it, then you can tell the answer. Here due to resonance, the C single bond double bond character loses, because you know aldehyde ketone shows nucleophilic addition reaction. Already we have discussed. It shows nucleophilic addition reaction as double bond breaks of ketone group losing double bond character of acid. So it does not show a taste like aldehyde and ketones. Aldehyde ketone shows nucleophilic addition reaction. This reaction is not possible in case of acid because due to resonance it loses double bond character. So this is very important property of what? Carboxylic acid. If you see the basic character, if you compare another example, that this is aniline and this is it is also one cyclic aromatic aniline. This is alicyclic. alicyclic amino compound and aromatic amino compound, and this compound is less basic character. Why? Because it has resonance which loses the lone pair from nitrogen. When lone pair decreases, electron density decreases, basic character decreases. As it has resonance, that's why it loses the electron density from nitrogen, that's why basic character is less. But in case of alicyclic, there is no such type of resonance possible. That's why it has more electron density than nitrogen, that's why more basic. So these are the some important properties of only related to resonance that we discussed in today's class related to resonance. So other type of effect we will discuss next class. After completion of all types of effect, then we will discuss some anomalous behavior, some exceptional behavior of organic compounds. Combined effect, all multiple effect is applicable to particular compound. We will discuss in the next class. Okay, thank you all.